Okay, so then it's my pleasure to welcome Damiano Anselmi from PISA, if I remember correctly.
Yep.
He's going to speak about the correspondence principle in quantum field theory and quantum gravity. So please.
Okay, thank you very much. In this talk, I will discuss the fate of the correspondence principle beyond quantum mechanics. So I will also talk about causality from a high-energy physics point of view, because we will see what the correspondence can be in quantum field theory and quantum gravity. And we will also discuss about our intrinsic limitations as human beings, because here the problem is to explore the infinitesimally small, really small, when we talk about quantum gravity, arbitrarily small, and that is a challenge because we are big. So we'll see that the best correspondence principle, I will argue, is made of these three: unitarity, locality, and renormalizability. Very conservative, as you heard before. And then you combine it with fundamental symmetries like Lorentz invariance, general covariance, gauge invariance, and other small requirements. But no causality is here. We see that out of this principle, quantum gravity will be identified in an essentially unique way, even better than the standard model. The gauge interactions are uniquely identified, but only in form. There is something we will not be able to fix here. And even worse, the matter sector is totally unrestricted. We do not have principles to predict what matter fields will be there at huge masses, high energies. And the major prediction of this is that you have to renounce only one principle, which is causality, but only at very, very small distances. So I call that microcausality. You renounce microcausality. So Bohr's correspondence principle is what? Is a guideline for the selection of theories in quantum mechanics. Basically, it just tells you that in some limit, which we call the classical limit, the laws should reduce to those of classical physics. Normally, it is the limit of large quantum numbers. In some cases, the so-called classical limit in quantum field theory has nothing to do with classical physics. In quantum chromodynamics, the classical limit is a Lagrangian of quarks and gluons, and that has nothing to do with classical physics. So you understand that this principle must be rephrased in quantum field theory. But you also might say, is it well posed? Is it useful? Is it necessary? Is it redundant? Is it a principle? Do we need it? Why do we need it? Shouldn't we just make experiments? And whatever comes out certainly will never be in contradiction with the laws we found before. It will just be a correction. So why do we need something like that? But you remember that everything we do, have been doing since a century, is a quantization. Quantization. The last part of this word means action in Latin. You do something. It's you're not looking for a theory. You have a logical process to build a theory out of the wrong theory. You start from a classical theory or something that you call classical theory. Maybe it is not, like in quantum chromodynamics, and you build the right theory out of a supposed limit of it.
Just a remark, there is of course a well-known counterexample to this, and that is Wigner's theory of the representations of the Poincare group from 1939. That is precisely deriving a quantum theory without any classical crutches. That is a term which was used.
That is possible. That is.
So you don't have to quantize a classical theory or classical Lagrangian.
Exactly. So that is a possibility. I mean, why should we do this? Why should we do this? So when you quantize, you start from something, you get to something else, you understand that there is some sort of correspondence. I will argue that to go to quantum gravity, yes, this is useful. We will see why, but it is also very, very risky. And if we do not have a correspondence, we will not have many chances to know the universe, apart from specific lucky situations. So the first thing is we do have a size. We do have a size. We are clumps of atoms. We are made of atoms. The atom has a size. The atom is the smallest ingredient out of which we are made. And if a clump of atoms, like a human being, wants to understand what happens at a billionth of a billionth of a billionth of the smallest ingredient it is made of, I really doubt that he is so omnipotent. So this is something we have to think about. Maybe we have some limits. For example, let's see some of our limits. Our eyes have a certain resolution. Has been estimated to be 3 × 10⁻⁴ radians. And we can move, we can get closer to an object, we can enlarge the environment which we can perceive directly. That's still limited, that's still not so large. We will call it direct perception range. Can we go beyond that? Of course, we build instruments. But in the long run, instruments can introduce errors and can propagate errors. And when we go down to the billionth of a billionth of a billionth of the size of the smallest ingredient we are made of, all the principles we are accustomed to might fail. Other numbers. The human brain can process an image perceived for around 10⁻³ seconds. This is optimistic. You can see it. We can call it the direct perception time resolution. Basically, we see the world as a video at 1,000 frames per second. It's not very much, but we can build instruments, and some instruments are fantastic. There are 5 × 10⁻12 frame per second cameras. They can show you light in motion. Dark room, turn on the light there, and you see it propagate. You can find the videos in YouTube. The shortest time interval ever measured is about 10⁻18 seconds, attoseconds so-called. Indirect measurements like the lifetime of elementary particles, now we go to elementary particles, are even smaller, shorter times, 10⁻25 seconds, but that is a little bit indirect. It's not really a measurement of a time duration. So even the concept of time, cause and effect, might be. So what we do when we build our instruments, if we see the world as at 1,000 frames per second, and we see that in this world we have cause and effects, while certainly we cannot assume that the principles we inherit from our environment break down just below our limits. That would be like assuming that the world conspires to trick us. So certainly they hold below those limits. Certainly causality will hold much below the dPTR, but we build our instruments on that assumption. We go and apply those instruments below that limit. We see that everything works out fine. No surprises. So we say this is an a posteriori validation of our assumption, which is causality. But even if we check that this works up to 1 billion of a billion of the dPTR, that still doesn't mean it will work forever. So we have to be prepared to this. So the question is, what is principle? What is universal and what is absolute? Of course, the answer is nothing. There's nothing we can claim applies to the whole universe. Otherwise, we are assuming that we are omnipotent. So that is why we may need a correspondence principle. That might be all we can get. And we might even be lucky if we get some, because I will argue that there are some sectors already where it can be proved that we failed And in my opinion, we will always fail. We will never answer the questions that certain questions that we have not answered so far. So, quantum mechanics is a lucky situation when the distances we explore are not so small. There is still some similarity, but then when you go down to smaller and smaller distances, the correspondence might fade and eventually disappear completely. Down to smaller distances, we have quantum field theory, and downer, you have quantum gravity. So let's see what happens there. Before going to the details, let's also describe this in another equivalent way. So I view it in the following way. We are living beings and develop our thought. Sometimes we overestimate the power of our thought, but actually every thought we conceive is just the product of our interaction with an environment. But that environment is classical. So our thought is classical, and it is totally inadequate to describe what happens at very small distances. It might be adequate, it might not be, but quantum mechanics already taught us a lot, because if we cannot even trust a verb like to be, existence of something when it is not observed by an observer, for example, then really we have to wonder how much we can achieve in this exploration and what the limits are. So whenever we apply the rules we learn by interacting with an environment to a different environment, we are assuming they are universal, but that is far from granted. So the indeterminacy principle and quantum mechanics already shocked us, and they are already enough evidence that down there we have an environment that is very, very different from the one that is up here. So there might be no principle that can really be trusted to the very end, and again, the correspondence might be useful in this, even if eventually it is doomed to fade away. So this is why we might find this discussion interesting. Although it is slippery, it is risky, we might be tempted to derail, to try principles that come are only from our human or personal tastes, like recent decades in physics spent to look for unification, grand unification, symmetries, supersymmetries, theories with no parameters, theories of everything, holography. Are these good correspondence principles? I don't think so. I think it's just like trying randomly without any clue. So the point is, the environment we wish to explore is so different from the environment we are placed in that the correspondence between the two is all we might get, but we have to be as conservative as possible. What worked in quantum field theory cannot be thrown away. Quantum field theory cannot be thrown away because it's the only thing that worked. So let's learn from it. What are the principles that worked so far in quantum field theory, and what will be the fate of those principles in quantum gravity? So the basic principles are unitarity, locality, and renormalizability. Unitarity is more or less a request of completeness. Say that a theory is unitary if no particle can appear from nowhere, disappear into nowhere, and probability is conserved. And it's just like saying there is no external, nothing external, no reservoir, nothing is given. You are describing really everything, the universe. Locality is already very delicate. Why do we require locality? No quantum field theory is local. There is no amplitude that is local. Again, quantization. You quantize a local theory. And that local theory that you call classical theory might not be a classical theory, like in quantum chromodynamics. So locality is a very powerful principle, and I will never renounce it, But again, look at what we are up to. Probably principles that we will never understand. Why is this principle? But so far they have worked. And I will even argue that if a principle is something we don't understand, it's even better. If we understood it, it would be too similar to our world, which is the wrong one, and too different from the one we wish to explore. So I'm not worried that these are hard to justify. I just proceed by success or failure. Renormalizability, another criterion that works, but it sounds like a recipe. But it works, so let's go on. Then we have fundamental symmetries, global Lorentz invariance, general covariance, local Lorentz invariance, gauge invariance. Then, analyticity. In quantum field theory, you hear that the S matrix is analytic. Well, it's not true. The analyticity of the S matrix is violated in many nice, interesting situations. There is some physics normally when you have violations of analyticity. This will have, in quantum gravity, we will have to renounce it in favor of region-wise analyticity. I will explain what it is. And it is related to another thing we have to renounce. In flat space, we have causality down to arbitrary small distances, standard model. But in quantum gravity, we will have to renounce micro-causality. The two things are actually the same thing. So let's see what we can do with these principles in the case of Yamme's theory. In Yamme's theory, locality, unitarity, and renormalizability tell us a very powerful conclusion. That is, this is the theory. This is the action of Yamme's. And actually, it also tells you, in parentheses, I add strict renormalizability. You could, renormalizability is too large because you can have also super renormalizability. But if you think about renormalizability in a strict sense, so the couplings are dimensionless, then you also predict that you will live in 4 dimensions. Well, this might seem powerful, but it is not, for a reason I will tell you in a moment. But anyway, Yamme's theory is fine with these principles: locality, unitarity, renormalizability, strict renormalizability, analyticity. I will define it precisely in a moment. Causality, and fundamental symmetries, which in this case are global Lorentz invariance and gauge invariance. But there is a but. This principle is powerful, but it's only powerful enough to determine the theory in form. There is no way we can predict the gauge group. Why is the gauge group U1 cross SU2 cross SU3, the list of the 3 simplest gauge groups we can imagine? Why there is no SU37, SU19? People have tried for decades to relate matter and gauge groups with unification principles, with many attempts like those. But so far, we are still with the standard model. There could be a periodic table with all gauge groups. Maybe they are all confined, and we will find them. Still, you see that we are entering into a sector of huge arbitrariness. Even worse is the matter sector of the standard model. That is completely arbitrary. There we are totally powerless. It's not very powerfully constrained by symmetries. So we basically have no clue about why it is what it is. The only restrictions we have is the low energy limit, and then you might know that there is an important constraint, which is the cancellation of gauge anomalies, which relates the gauge group and the matter sector. But these constraints are so weak that you can find infinitely many solutions. You can add arbitrarily many heavy particles to your standard model. And that means that going to smaller and smaller distances, we are basically powerless. So is this the sign that the correspondence has already faded away, and that there is a sector that we have not been able to restrict, and probably going down and down, we will never be able to restrict? Is this a sign of our limits? Now let's go to quantum gravity. In some papers 1 year and a half ago, I proposed a theory of quantum gravity following these principles and renouncing the smallest amount of principles possible. And I will describe it to you. Recently I published this review. If we want, you can also find there an address to the previous papers and what is done there. And to do so, I had to go back to the very basics of quantum field theory, which is the very first quantization step you take, which is the free particle, the quantization of the propagator, Feynman propagator. If you have a propagator 1 divided by p squared minus m squared, you normally use this prescription, the so-called Feynman prescription, which is what describes a physical particle. Namely, in the complex plane of the energy P0, you displace the two poles of p squared minus m squared, the two zeros of p squared minus m squared, you displace them there. And then when you calculate loop diagrams like a bubble diagram, you integrate on the real axis. That means that you leave the left pole above and the right pole below. That is what defines a physical particle. Okay. Good, fine. What if I change the sign in front of the propagator? Then I have a ghost. That's an unphysical particle. It violates unitarity, or you can rephrase that violation as negative probabilities, or in many, many other ways, but it's always a huge, huge problem. Well, that minus sign would be very useful for gravity, because with the help of that minus sign we can renormalize quantum gravity. But if you do that, you renormalize quantum gravity and you lose unitarity. So let's go back to the principles. In the case of quantum gravity, so far, which means before the theory I proposed 1 year ago, these two were mutually excluding each other. Either you have unitarity or you have renormalizability. Unitarity is, for example, if you quantize Einstein gravity, that's unitary, that's non-renormalizable. And renormalizability you can achieve with a higher derivative gravity. We will see the Lagrangian, because it is the same one as in my theory, but quantized in a different way. You have a higher derivative theory which propagates ghosts. So it's renormalizable, because there are higher derivatives that make it renormalizable, but it is not unitary. Okay, so to see what the key point is here, is it's very ambitious and very bold, you see, because you have to change the very basics, the first chapter of quantum field theory. You touch that prescription. The bubble diagram, if you compute it with a Feynman prescription, it's a loop integral, two propagators like this. Well, you will see that it gives a function that from the mathematical point of view is an analytic function, which is analytic everywhere in the complex plane of the energy, for example, up to two branch cuts, which are on the real axis when epsilon goes to 0, or a little bit displaced from the real axis when epsilon is not 0. But that's it. The two branch cuts are the violations of analyticity of this amplitude, and they have a physical importance because they tell you when a physical process takes place, which is when you can create the two circulating particles from the external particle. You need a threshold to produce. The energy must be larger than the sum of the masses here. And this branch cut has a physical meaning. Okay, this is just a review. So the key is here a new quantization prescription. Basically, I now show you how you can turn this pole, or the propagator, in something that is neither a physical particle nor a ghost. It's a fake particle, which I call a fakeon. And in that case, you have renormalizability and unitarity. But the only price is microcausality. A fake particle is a particle that simulates a real particle anytime you do not see it directly. It mediates interactions. But when you try and look at it directly, you cannot see it because the scattering, the transition probabilities to produce it are zero. So basically, you take this propagator, and instead of using the Feynman prescription, you multiply above and below by p squared minus m squared, and then you add this kind of width. Let me call it width. In the end, we will take epsilon going to zero, okay, but in a new sense. This is the corrected propagator. Now, you are already suspicious that this propagator doesn't propagate anything, because on shell, which means that p squared equals m squared, it vanishes. So if on shell it vanishes, it propagates nothing. This one on shell blows up, because you see on shell this one is 1 over I epsilon, and epsilon goes to 0. But if you take epsilon different from 0 and calculate this on shell and then take epsilon to 0, this is 0. However, this is not to be taken as you see it. You have to take it in a new sense, and in fact, this investigation started from with Marco Piva, a PhD student who is present here, from the so-called Leipzig models, where epsilon is finite, and there you learn something crucial. You learn that there is a reason why this distribution has never been studied. The point is that if you take it literally, you would integrate, you have 4 poles now. These 2 poles have been split into 4 poles, but if you take it literally, you normally would integrate on Minkowski in between the pairs of poles. This generates bad non-local divergences, which I proved with a colleague in Rome, Uguaglietti, before the beginning of this investigation. And that's why I turn to these Leipzig models, because they suggest you to come from the Euclidean. And if you come to from the Euclidean, the prescription must be this one, to integrate in this funny way. The left pair remains above, and the right pair remains below. Exactly as you do for the Feynman prescription, with the difference is that the pairs are not split. The poles are not split into pairs. You see, the left pole is above the path, and the right pole is below. So that's why in that case you can integrate on Minkowski. But it is equivalent to integrate on Euclidean. Here instead you have to really prescribe that. And we also found that the Leipzig models, as formulated by this prescription given by Lee and Vick 50 years ago, were not formulated completely. Indeed, this has problems, I will describe in a moment, and we had to complete the formulation, and that led to everything else. Why? Okay, because do that, so you integrate the energy of a loop diagram. So you take your bubble, you have an integral here, and that integral you split into the integral on the loop energy and the loop space momentum. But after you integrate on the loop energies, those 2 poles, the analytic structure that normally is just made of those 2 branch cuts. The poles become branch cuts. Well, in this case, when the width is finite, non-zero, those branch cuts blow up and then become large finite regions. Inside those regions, very bad things occur, Lorentz invariance is violated, and analyticity is violated. So that was the status of the Leibniz models. But you can show that this region can be shrinked onto the branch cuts by deforming the integral on the loop space momentum. So here you have an integral on a loop momentum, which is split into an integral on the loop energy. You follow Leibniz, fine, but then you remain with an integral on the loop space momentum. Then you have to follow the other half of the prescription, which we formulated this way. So basically, this is the new thing you do. The new thing you do to calculate with this prescription. You have this enlarged regions instead of branch cuts. You go inside, which means you choose an external energy here. You calculate the integral. The integral is not analytic and not Lorentz invariant. Then you deform the integration domain on the loop space momentum. You shrink that region. The limit is analytic and Lorentz invariant. And actually, it is very simple. The limit coincides with the arithmetic average of the two analytic continuations from above and from below the cut. And that is the violation of analyticity, and that is the violation of causality, for the reason I explain now. So basically, it's the Feynman prescription says you displace the branch cuts, and then on the real axis, here you are above, and here you are below, one of the two only. When you do this instead, it's like going inside the branch cut, calculating inside the branch cut. And this is suggested by the fact that this is a large region, so you calculate inside, then you take the limit, so you are still inside here. And what you get if you calculate inside is exactly the average of two analytic functions, which is not an analytic operation. So you have two functions now, one in this region of the complex plane, one inside here, and that you can prolong analytically to an extended region. I will write it as a cone just to be explicit. So this is how I describe analyticity and region-wise analyticity. Normally you have analyticity, which is this one. You have two branch cuts, and either you go from above, that's the amplitude, or from below, that's the complex conjugate amplitude. This branch cut is a physical process, and it corresponds to a production of two particles. Here, you have those branch cuts are enlarged into, let's say, two cones, anything you want, because you're just interested in the real axis in the end. You have the Euclidean region, the region of the Euclidean axis, which is here. There you can compute everything as usual, as here, doesn't matter. But then you have to jump inside here, and that you cannot do analytically. You have to do it by means of an analytic operation, which is the average of the two analytic continuations. In the end, what you find on the real axis here and inside this region is another analytic function. So you have an analytic function for this region, and here you have another analytic function. But the analytic function inside is uniquely determined from the analytic function outside, not vice versa. By this operation of average, which is not reversible. Instead, normally you have analyticity, which means as follows. If you compute your amplitude of Feynman diagram in an open set, any open set, you know it everywhere by analytic continuation. Here, instead, if you compute it in an open set of the Euclidean region, you still know it everywhere, but not by analytic continuation. Analytic continuation is enough in the Euclidean region. Every other region you reach by means of the averages. So when you make this average, you do not produce imaginary parts. You might remember from textbooks that in this branch cut, there is a jump of the imaginary part, a discontinuity of the imaginary part. Here instead you do not have any discontinuity of the imaginary part. That's why you do not have a physical process. That's why here you see, as I said, you have a physical process because you really have a branch cut. Here you do not have a physical process, but you have something. That's a fake physical process. But the point is that in this case, when I have a physical process, I cannot change the sign in front of the propagator because that would lead to a ghost, which is a physical, unacceptable process. Something you should see that is predicted to occur, a ghost, but it's not acceptable. Here, instead, I can change the sign in front because a fake process of one kind becomes a fake process of a different kind, but it is still fake, and no impact on unitarity is generated. So the discontinuity of the amplitude disappears, because the operation is symmetric with respect to refractions to the real axis, because of the average. Again, this is a symmetric operation. That's why you do not generate imaginary parts. The amplitude basically is real here, and it is real there. And this is the classical action, and we'll see its new features now. So first, it is a higher derivative action. It is uniquely implied by the principles we said before, unitarity. So in this case, unitarity, renormalizability, and locality. And let's assume that we are in 4 dimensions, implies this as the unique action, and also implies how it should be quantized. Because if you quantize this action a la Feynman, this gives a theory that is known as stellar theory, that was considered in the 70s, 1977, I think, and it's not unitary. But now you have an option, which means that if you rephrase this Lagrangian, instead of using higher derivative, you can introduce Lagrange multipliers and go down to normal derivatives. Then you will see more clearly what kind of fields it propagates. Well, it propagates the graviton. Let's say that's the metric. But then there is a massive scalar, and then there is a massive spin 2 field. The massive spin 2 field is the one which has a propagator with the wrong sign. That's why normally it is a ghost. Now you quantize it in this new way, it becomes a fake. That's it. The theory changed completely, the predictions changed completely. And there is a funny thing, however, because what happens is that you still have these fake particles, the fakeons. They mediate interactions. They simulate a physical particle. For example, let's suppose that the muon were fake. It's not fake. Let's suppose the muon were fake, but the muon decays. If I just check the decay product of a particle, I cannot distinguish it from a fake. I really have to see if the particle exists or not. The muon can be seen directly, and so it is not a fake particle. Which means basically that it is consistent to project the fake particles away from the physical spectrum, and indeed the final theory is the one that you obtain by combining all these things I told you. So the new quantization prescription, the projection, and then you have an S matrix that is unitary in the projected subspace, because it is not unitary in the whole subspace. But then there is a funny thing, going back to our correspondence principle, that this is not the classical action anymore. That's why I call it interim classical action. It means that the true classical action, the true classical limit, has to be found from this one by projecting away the fake particle, using the prescription we saw, using actually classical limit of that prescription. So this is not the classical limit. And when we require locality now, I'm not even requiring locality of the classical limit. I'm requiring locality of the interim classical action, because the final classical action is non-local. How? It's simple to describe it. Basically, you take this action, classical. Now what I'm saying is inherited from the quantum theory, from the quantization, but now we can work classically. You take this one. You work out the field equations for this field. You solve them with the prescription given before, this average prescription. Imagine you solve it, because it's difficult now. Now we are trying to do that, but imagine you solve it, you insert the solution back, and that is the finalized classical action. So the correspondence principle now here works in this funny way. You have an interclassical action, you quantize it, and then you classicize back the quantum theory, and you find the true classical action. We include the corrections that I predict to the Einstein equations of general relativity. Because now, if you do that, you will have complicated equations, but I tell you how they look. And in the paper you can find that explicit form if you want to join us in searching for solutions now. This is the form of the equations. Basically you have that the Einstein tensor r mu nu minus 1/2 g mu nu r is equal not to the stress tensor, but to a certain average, which is an average that is sensitive to a little bit of future. That is where you violate causality. Let me give you a toy model which is very visual. You can see it, the idea. Toy model, take a Lagrangian, m divided by 2 velocity squared minus potential. Then you add higher derivative correction, some constant tau, and the acceleration. You do everything I told you, and then you will find a kind of equation of motion that looks like this. ma is not equal to f, but it is a certain average of f, where you have a certain green function, which is a distribution, the distribution reading here, which is strongly oscillating, and it tends to f equal ma in a certain limit where you drop this term correctly, but it is uniquely fixed. So you have a uniquely fixed equation which tells you basically everything. That is how causality is violated. So it means that if F is the external force, you need to know, anticipate if you want, the external force for some little bit of future, because this strongly oscillating factor will average the information to 0 in the far future, but not in the close future. So to write down your equation and solve it, you need literally to violate causality. And that means that down at very small distances, past, present, and future, and cause and effect will have no meaning. And you can say, you can ask me, what are these distances? How do you? Okay, these distances. Yeah.
What do we learn from this? I mean, we know this is not the correct Lagrangian.
Why do you say it is not the correct Lagrange?
No, I mean, usually for
Well, usually.
Take this.
You have to say usually. That's the whole point. I claim that this is the correct Lagrange. I claim that this is the correct theory. This one, of course. This is a toy model. I not only claim that it is the right theory, but I claim that these violations are detectable. And not only I claim that this is the right theory and these violations are detectable, but I claim that this is a unique theory. It is the one.
I still don't get it. I mean, for classical mechanics, obviously we don't use this Lacan.
Yes.
Would you like to postpone the discussion because there is a remark here about the Teufel?
I'm almost over because I planned 45. You told me 45 minutes. Yeah.
Yeah, that's nice. I mean, because, yeah.
So there is one transparency. We have plenty of time, I think, for discussion. What was I trying to say? I had something to say about what you said, but now I forgot. Okay, so, yes, good. Now, you can ask me, what are these distances where causality will break down? So, by the way, what I'm saying is that you have always been using this theory, but since tau is small enough, you have always been using this theory, but since tau is only small enough, you have never seen the correction. That's basically, anytime you discover new physics, this is how it goes. Galilean relativity is Einstein relativity with c equal to infinity. Anyway, what are these distances? They are rooted in these parameters. Basically, you have violations of causality at energies greater than the mass of the fake particle. The mass of the fake particle is the energy at which everything changes. That mass is a combination of these parameters. I think I remember by heart, and it should be something like m chi is equal to zeta divided by alpha. Zeta is the coefficient in front of the Einstein term. Alpha is the coefficient in front of this combination, which is Weil tensor squared. And what is the value of this mass in nature? We don't know. But first, it might be much smaller than the Planck mass, without disturbing any observation we have made so far. That could mean 10 to the 12 GeV, but could be even smaller than that. It might be too large for making experiments in high energy physics and detect these things in high energy physics. And that's why I'm concentrating on these, you might say, complicated corrections to the field equations, because these are new equations that can be treated exactly in principle or non-perturbatively. These, in principle, can allow us to study amplifications of this effect, the amplification of the violation of causality, in order to see some effects. We have to plunge into this work, study. We're doing that right now. Maybe new students will join. Actually, certainly new students will join. What is the form of a new black hole? What is the universe predicted by this? And so on and so forth. So, the indeterminacy principle is down there. It's very, typically it is at the atomic distances, but we can amplify it to our distances. Anytime we make an experiment of quantum mechanics, that's what we do. Because a generator of random quantum numbers, random number generator, does precisely that. You let an atom or a photon decide what's going on in your display, 0 or 1. You amplify that. So, if you combine, there is another sign of the violation of microcausality. I mention it here because that concerns only high energy physics, and I still doubt we will be able to show it. It is that the width of this fake particle is negative. Well, that means precisely that we violate causality, because when the width of a particle is negative, you could say the lifetime is negative. No, that's not true. It's simply that the lifetime sees the future instead of the past. It's just a game. But this is very hard to detect, because I asked phenomenologists, no width has ever been checked to be positive. Nobody ever thought about doing that. We only have experiments that tell us that the absolute value of the width of the particles of the standard model are such and such numbers. Nobody measured the sign. It's very difficult, apparently. Simple things can be very difficult. Anyway, this is the theory. You can add to that the rest, the standard model, covariantized in curved space. And what are the principles? They are unitarity, locality, and renormalizability. Then renormalizability is, I call it proper renormalizability, is a refinement of strict renormalizability. Strict renormalizability is still not precise enough because it doesn't tell me which couplings are dimensionless and which couplings have positive dimensions. And since they are preferred couplings, the gauge couplings, those, here is the definition, those have to be dimensionless in gravity and in Yang-Mills. In Yang-Mills, the gauge coupling is dimensionless. In the standard model, all gauge couplings are dimensionless, and the same in gravity. That's why this theory is unique. So this seems to be the reasonable thing. Again, you might like other principles, but they are too rough. We didn't have the need to refine them too much in the past, but now there is that need to be precise. You have fundamental symmetry requirements, global Lorentz invariance, general covariance, local Lorentz invariance, and gauge invariance. You renounce analyticity, you have only region-wise analyticity. You renounce causality, you only have macro causality, but you give up micro causality. So in terms of light cones, it means as follows. It terms that you can, your future is not only determined by the past, but also by some small hyperboloid in those spatially separated regions. So this is not like violating Lorentz invariance. Lorentz invariance is perfect, but many people have groups have looked for bounds on the violation of Lorentz invariance, and they have checked. They ran into these kind of situations and problems. So I will propose to them if they can convert their analysis to this to put bounds on the masses of the fake particle. A curiosity to end is that we have a solution in every even dimension greater than 4, not only in 4, even in even for Yang-Mills, that is f instead of f squared, there is a polynomial here, and the extra derivatives generate fake particles. So, well, how do we know that we live in 4 dimensions? Of course, at large distances, we live in 4 dimensions, but it might be that at small distances, there are, we discover that we live in higher dimensions, which, however, would have to be compactified. And from the perspective of our 4-dimensional low energy physics, that would mean having infinitely many fields, infinitely many tau of infinitely many fields. So if you stick with locality, unitarity, renormalizability in this sense, having a finite number of fields at least, it's a very small, and the only requirement I put on the matter sector, which I stress again, is totally unrestricted, almost totally unrestricted. This is something that should bother us. The matter sector, we have no clue how to restrict. At least if you demand that there are only a finite number of fields, the result is unique, and it is the one I told you here. Thank you very much.
Thank you very much for your talk, and we have time for questions. Yes?
I have a comment and a proposal. The comment is all what you said applies also to Yang-Mills in flat space-time.
Yes,
okay.
To every theory.
There, the standard way to quantize the Yang-Mills theory is yeah, of course. You have a kind of pre-Hilbert space, a Klein space, which is of course totally unphysical. And then you form the physical states out of them by using your gauge, I mean adapted to your gauge, which is taken care of by the Biar's transformations. And then you factorize the Klein space or the pre-Hilbert space, the Fock space, the E Fock space, be factorized by the states, which are relative norms and vanishing norms. Okay? In that way, you get that order Hilbert space. You do not violate Lorentz invariance, and everything is okay. Good. Now, my claim here, or my proposal is, you add to this Lagrangian, to this classical action, you add, after you have done you first take a gauge fixing, and then you add the corresponding Fourier fields. Of course, you can do it, technically you can do it in different ways. And you end up then with a theory which has reproduces precisely what you, not precisely what, equivalently, what you derive with your fakeon. But you have a new thing, namely, you have to construct a physical Hilbert space, and then the observables which you write down or want to calculate, they of course have to be constructed in a way that is compatible with BR's invariance. So your energy momentum tensor, for instance, contains of course contributions from the finite Popov fields, and also there are terms mimicking the curvature and so on, built up from the finite Popov fields. I mean, they come along with covariant derivatives, stuff like that. And therefore, only on that basis, you should then start doing calculations and asking now, is that unitary? It has to be, otherwise it's nonsense. But is there perhaps locality in one sense or the other? And that there, of course, I agree with you. There may come difficulties because the notion of locality becomes perhaps difficult to understand in this not only because of the Faraday Popov, but because you're on a curved spacetime. And but still, I guess that is a completely satisfactory answer at the end if one has gone through all of this. Once you really use that, and again to the classical limit now, the classical limit is non-trivial. I would say. I mean, what one has to identify with what one sees in classical relativity, general relativity, that is of course a question of new analysis. This is not obvious at all. This is also not obvious how locality or causality is realized. Let me give you an example. People doing
just maybe let me. Do you want to respond, or I mean, because
I wanted to ask you if you are thinking of a new kind of Faraday-Popov structure for the fakeons, or you are the usual one.
Just for this.
Well, of course, we have didn't mention we have just a couple of papers with Marco with the complete one-loop calculations, checks of unitarity, calculations of the width, which is negative. All you can find already done with all that stuff. But somebody proposed to me, if this fakeon can be seen as a sort of Faraday-Popov ghost, which has to be projected away. Maybe yes, but there is one thing. Can I comment on that? Then you can. There is one thing. So yes, you can see this is a very good point. Thank you, because you can see this as a sort of gauge-fixed action. Interim classical action. It means that it is still unprojected. You have to project something away. But that is not a Faraday-Popov ghost. So maybe we will try, or you can try to find a more evolved formalism. But for one reason that I tell you now, this is not that. There is something. If you consider the Faraday-Popov ghosts in Yan-Mills, for example, you have a symmetry, the gauge symmetry, and you have gauge independence. You know that you can go to a gauge, that is the Coulomb gauge, where you project them away completely. Wait. That means you project them away completely, not only from the initial and final states, but also from inside. And indeed, you do not propagate those. These cannot be projected away completely because they leave this remnant, which is the violation of causality. In that case, you don't have that remnant, and you have causality.
Okay, I do not agree with the Coulomb gauge case, because there you have zero modes.
Let's take UED, for example, which is under control.
It's precisely the same problem there. Also there, the Coulomb gauge is not completely well defined.
I know, but I know that. I know this kind of. You have to do it as a limit of another gauge.
May I suggest that? I mean, this seems to be something which you have to work out. But for the sake of that, if there are other questions, I mean, I don't want to interrupt you, but
No, it's okay.
Maybe you need a blackboard. Yes,
Could you specify what you mean by negative width? Is
Yeah.
t index type less than 0?
Yeah, good. So basically, if you have a bright Wigner, let me do it for a rest particle. Oh, sorry. Then if I remember correctly, there is nothing here, just like that. Let's do the Fourier transform of this, positive or negative. You will see that this is e to the minus gamma t divided by 2, but in front there is a theta function that is theta of t or minus t, depending on gamma. Which means that, of course, the Fourier transform is always a damping exponential. It cannot blow up. Because it is a Fourier transform. You cannot map an L1 function into an exponential that grows. But you have in front the theta function that picks the future instead of the past. That's it. So that's the meaning of a negative width. If you use this as a green function, you will have that your source, you have this green function, then you will have something like the integral of t minus t prime some source, dt prime, minus infinity plus infinity. You have that to know your field at time t, you need to know the source in the future now, not in the past. That's it. And gamma, 1 over gamma, tells you how much future you need to know. Basically, because it's an exponential.
there's a question in the back, and then, so there are many questions now. But
Can you help me with the rigorous definition of region-wise analyticity? What do you mean by that?
Yes, it means that the space of momenta, so I take an amplitude, it depends on external momenta. The complexified space of external momenta is divided into disjoint regions, and your amplitude, you have to fix your amplitude, or Feynman diagram, take one Feynman diagram, and the space of complexified external momenta is divided into disjoint regions, and the amplitude is an analytic function in each of them, but there is no analytic way to relate the function in one region from the function in the others. There is a non-analytic way, which is unambiguous, however.
What is the region for you?
A subdomain, an open subset of the space of complexified.
An open.
Yeah.
But it means you have disconnected.
Disconnected.
There is a
But
concept
then
of
it's
Riemann
then,
circle.
then, then if it's analytic in disconnected object, then it's analytic in total.
If it is analytic in disconnected objects,
An open disconnected object.
well, what do you mean?
yeah.
Maybe you have to go to a Riemann surface to have the full.
Well, I mean,
When you have cuts, then there is a corresponding Riemann surface, and you need
these are disconnected regions, right?
Yeah.
So I have one analytic function.
If you have a function that is analytic on the one side and on the other side, then the function in the union of these domains is again analytic. So. Yeah, but he said he decomposes the whole space into two regions. Well, this means the full space is the union of these two regions.
If you want, yes. Let me give you an example so that I clarify what I mean. If, for example, you take the function square root of z that has a, let me put the branch cut here. Then instead of describing this function in this way, as we normally do, you describe it as this way. You enlarge this region, and you take the average of the two analytic continuations of the region that you have from here, from above and from below. So outside you have the square root of z, and inside you have 0. that you can call an analytic function defined region-wise, if you want. In total, it is an analytic function, but it's not what is normally done or meant in quantum field theory as an analytic amplitude. Okay? So I understand your...
I didn't get the construction.
The construction is that if you take the square root of z and you go here, you will have minus something from the above, plus from below. The average is 0. So you have an amplitude. This is a bubble in 3 dimensions, by the way, which is then in physics.
No, I didn't understand. Probably we discussed it.
Maybe you have.
But I understand your
right
point. Yes,
bit.
if you want, you can call it analytic. But in physics, it wouldn't be called like that. Yes.
So there were further questions.
So that's why I have to be precise on that.
I just wonder what this fakeon is. So it's not a real particle, but it's also not a ghost. So how can one understand this? I mean, this is nothing which can be observed directly or detected.
No, it can be observed indirectly, and for example, by the predictions. If you have corrections to the equations, you can observe the presence of this by the how it affects the equations, the other equations of motion. Maybe you were asking something more specific. What is what you? If I can give you an example from standard model. I don't claim that the Z boson is a fake particle, but the Z boson, as every other vector boson, has never been observed directly. We only see the decay particles. From that, I cannot tell you if the Z boson is fake or true. But the muon is that because in accelerators you have something like this. At LEP, E plus, E minus, Z, something else. Okay? That's what you observe. This, you don't observe Z. Never seen that. You don't observe Z, you don't observe Ws, you don't observe the quarks, you don't observe the gluons, and you don't observe Higgs.
So there was another question in the middle. I don't know if it's resolved. Or do you want to respond?
Related to the previous question. It's like asking this similar question in another format. So what's your proposal? What's its relationship to other approaches to quantum gravity? For example, is it compatible with string theory? It seems, we have under strings. If string theory doesn't contain fakeons, then
I think that everything is compatible with string theory.
So then, is the fakeon like a part you want to add in string theory, or?
I've never cared about string theory. Really. I'm sorry. I think it's one of the many derailments of recent physics. I'm not interested in considering it. I don't take it seriously. I don't care about string theory. So
Maybe one, or you want to respond?
So then maybe let me phrase it in another way. So in usual Feynman diagrams, many people interpret this as calculational tool. I mean, the virtual particles, they don't have to exist in nature. So what about fakeons? Do you think
this is a virtual particle that really doesn't exist in nature? Because it's true that it is virtual, but there is the optical theorem, which is just the unitarity equation SS dagger equal 1, which tells you that the imaginary part of the amplitude, which is that discontinuity, is a certain cut diagram where you are going to check the transition probability of producing the virtual particles as real particles. So even if they are virtual, there is always the chance to make it then real. That's why the projection I'm talking about is highly non-trivial. I cannot throw away something from the initial and final states because this theorem will generate them back from in between. In between, everything that is virtual, that's what unitarity says, that's the completeness. Everything that is virtual can become real. That's it. That's the good point.
So maybe the final question?
Does your description with the force water pool improve the Lee-Wick model?
Yes, because this, indeed, this action is not a Leibniz model. That's why I had to come up with this prescription. The first Leibniz model you have from quantum gravity would have to, is one of these types, but in D equal 4. It would be R plus Ricci, box Ricci. The higher derivatives. The first Leibniz model needs more higher derivatives, but then it violates the principle of having a dimensionless gauge coupling. They are super renormalizable theories, and they are infinite dimensions.
Okay, so then let us thank the speaker again.